We're going to start out chapter 3 with the emphasis on more derivatives, and in order to do more derivatives we need to have a good review of the chain rule. That chain rule enables us to do derivatives of exponential and logarithmic functions and things we haven't seen yet. So let's talk about what it means to apply the chain rule in a derivative situation. Like I said, it's useful for composite functions. We'll see it both in the prime, which is Newton's notation, and Leibniz's notation. We'll see it as it affects power functions and also related to trig functions. Most often, the chain rule is written with nested composite functions, where you would have f of g of x. And so we call one the outside function and one the inside function. And so the chain rule says that you start with the outside function and you take its derivative, but you leave the interior function unchanged. And then you multiply, which is where the chain comes in, because you're forming links in the chain. You multiply by the derivative of the second function. If you're using Leibniz notation, you are going to be using dy du followed by du dx to get yourself the derivative of one multiplied by the derivative of the other, which leads us to the chain rule that can be applied for any number of nested functions. So if your composite function had 3 and you were taking the derivative of that, then you just again stay in order. You take the derivative of the outside while leaving the inside unchanged. And then multiply by the next successive derivative, so g prime, leaving the next interior unchanged, and then a third link in the chain, h prime, and then the derivative of the inside, which is just 1. So most often we refer to that as the inside-outside rule, working on from the outside and working your way in. So if we're asked to differentiate this trig function, the outside function is the cosine function, so we'll start with that. And then the inside function would just be the quartic function. And so we show d dx that we are applying the derivative rules to this function. So we'll start with the outside. The derivative of cosine is negative sine. 3x to the fourth minus 2, and then the chain on that would be the derivative of the quartic function, which is 12x cubed. And so to put all that together, you would say negative 12x cubed written in front of the quantity sine 3x to the fourth minus 2. So this should be familiar with what you do last year. It seems like a simple thing, but I can't tell you how many times it was oh, you forgot the chain rule, you forgot the chain rule. So it creeps up even though it should be, it's an easy process, we just often forget it. The chain rule can be used multiple times. I find it most helpful to rewrite radicals as a rational function instead with a rational power. And so you'd write that to the 1/3 power instead. And then you're going to identify that your outside function is that 1/3 power first, and then you're going to work your way in. So dy dx would be the outside function of 1/3 times the interior of the sine of x squared, and then we reduce that power to negative 2/3. The next link in the chain would be the derivative of sine, which is cosine, leaving me with x squared, and then finally the derivative of x squared, which is 2x. So overall, you would simplify that in the following way. You would say my numerator is going to be 2x cosine x squared, and then the denominator would lead off with the 3, And then we're going to express the sign. You can leave it like this, the sine of x squared to the positive 2/3 power, or you could express that with a radical. Both are acceptable, so that you would express that as the cube root of the quantity sine x squared, and that whole quantity is still being squared. Or you could put the square right there instead. Either way, both are fine. To finish up, we'll look at this cosecant function. And again, I would encourage you to write that as the cosecant of the quantity 5x cubed minus 2 and that whole quantity squared. So then when we want to find y prime, the 2 is going to be our outside function. So it would be 2 in the front, the cosecant of 5x cubed minus 2. The next chain would be the derivative of cosecant, which is negative cosecant cotangent. So we'll have negative cosecant of 5x cubed minus 2 times cotangent also of 5x cubed minus 2. And then we have another chain, which would be the derivative of 5x cubed minus 2, so 15x to the second. So when we simplify all of that, we'll have a negative out front. 30 is going to be the coefficient, x squared. And then we're going to have two cosecant expressions. So I'll say cosecant as 5x cubed minus 2. And then finally cotangent of 5x cubed minus 2. Now you can use this chain rule to find tangent lines, to find normal lines, to find horizontal tangents, to find vertical tangents. All the same rules, you'll be applying your chain rule derivatives, and then you can use those to find anything else we've found with derivatives before. Velocity, acceleration still apply.